Hello, my name is Zachary Brownstein, and I'm in the Chemical Diagnostics and Engineering Group within the Chemistry Division at Los Alamos National Laboratory. And the title of my talk is Developing Filament Feedstock of Polymer Composites for Additive Manufacturing. For many years, we've heard about a revolution in 3D printing, yet manufacturing with the technology has not come to full fruition. One reason for this is because the range of materials available is too limited, and that problem is what drives this project. I'm interested in making composite materials for additive manufacturing. And one way composites can expand the range of applicable materials for 3D printing is to add functionality. Functionality can come in the form of incorporating metals and alloys, drugs and antimicrobials, wood, ceramics, or radiation shielding. As an initial step towards developing a new material for additive manufacturing, I wanted to pursue radiation shielding, specifically gamma radiation, because current technologies in both the commercial and research spaces are severely lacking with regards to feasible and accessible radiation attenuating 3D printing filaments. Traditionally, shielding gamma radiation has been performed using lead. However, because of its serious deleterious health effects, we are trying to move towards other materials. It should be noted that if we can successfully fabricate a radiation shielding filament, then this has the immediate scientific and tangible benefits for ensuring worker safety and equipment and instrumentation function. Within the realm of additive manufacturing, the most common technique is fused filament fabrication, or FFF or 3F, whereby a filament is heated past its melting point or glass transition temperature and structured layer by layer into a full part. On the right is a photo of the 3D printer we used, which employs 3F. My goal in this project is to first develop a high weight % loaded polymer composite that can perform as a chemical resistant radiation shield. This will be performed by using a base polymer, ABS, a terpolymer standing for acrylonitrile butadiene styrene, a common 3D printing polymer, and incorporating PVDF, polyvinylidene fluoride, a polymer that can better withstand organic solvents and acids, and bismuth, a metal that can shield against gamma rays. After this is complete, our efforts will be focused on creating homogeneous and smooth filaments that are able to be 3D printed. Once these multifunctional filaments are fabricated successfully, we will move on towards creating polymer composite filament feedstocks for other applications, thus expanding the range of possible 3D printed materials. Following the development of polymer composites, the filaments will have their material properties evaluated via thermal, mechanical, radiative, and chemical analyses. The general scheme for developing composite filaments can be broken down into 3 steps. First, the base polymer must be dissolved in a suitable solvent. Then, fillers in their desired proportions can be incorporated into the polymer solution. Finally, the composite is fed into an extruder to create filaments. The image on the left is of the extrusion instrument we use, where the composite materials are fed into the hopper, which is on the opening on top, and a heated metal screw pushes the material through the nozzle to create the filaments. On the right, there are examples of filaments we created using this method. The top image is of an ABS PVDF 50 by 50 weight % filament, and the bottom is ABS bismuth 50 by 50 weight % filament. These are of constant diameter and smooth enough to be fed into a 3D printer. Once we were successfully able to fabricate ABS composite filaments with PVDF and bismuth separately, all 3 were combined in different proportions to make a variety of printable composite materials. The FTIR image on the left shows peaks associated with the functional groups of each organic component. Observe that the top black curve representing ABS has peaks that all the other curves exhibit. thus demonstrating that ABS did not degrade in the process. Also note that the bottom two curves have all three components, and that a peak characteristic of PVDF around 1200 wave numbers, which corresponds to a carbon-fluorine bond, is only exhibited in the filaments with PVDF. The XRF image on the right shows a color mapping of elemental bismuth in a cross-section of a filament at an angle. Using these two techniques ensures that the polymer and metal fillers have been successfully incorporated into the ABS matrix. Testing the radiation shielding capabilities of the composites was performed using a cesium-137 source emitting high energy gamma rays at 0.66 mega electron volts. Reviewing the radiation attenuation chart of bismuth shows our attenuation coefficient is here, and inputting this as mu along with the incident radiation I, density ρ, and thickness T of our samples allows us to estimate an attenuation of 13% when we measure an attenuation of 15%, which is in pretty good agreement. Once we were able to successfully make radiation shielding filaments, we designed filaments for other applications. For more radiation-based composites, tungsten was used instead of bismuth, and for shielding neutrons, filaments with polyethylene and boron were used. For medically based composites, the biocompatible polyethylene glycol was incorporated along with the antimicrobial ceramics zinc oxide and titanium dioxide into a PLA polymer network. The images on the left are cross-sections of the multifunctional antimicrobial filaments. We observe an outer crust developing, which becomes more pronounced when PEG is added, along with some concentric patterning within the filaments. This work is currently ongoing, and further developments will yield insight into this phenomenon. To test the antimicrobial activity of the filaments, we placed and covered the specimen in soil for a prolonged period of time at constant humidity and temperature. Some results from this experiment show that while various microorganisms can tear and alter the PLA filaments, they are less successful at thriving on the filaments with ceramic fillers. I would like to thank the Los Alamos Mission Foundation and Institute of Materials Science for fostering an environment of innovative research. Work would not be possible without my Los Alamos National Laboratory mentor, Andrea Laborio, or my University of New Mexico advisor, Heather Canavan. I'd also like to express my gratitude towards Samantha Talley, Joseph Dumont, Jianxiao Zhao, and Quansu Li for their insightful discussions furthering the research. We are able to publish the first part of this research as an invited featured paper in the Journal of Materials Research. If you are interested in reading this study, you are able to find it at this web address. Thank you for attending my talk.